Hi guys, today we're going to talk about the natural base e. Now e is a number like pi. E is an irrational number, which means it never repeats and it goes on forever and ever, just like pi does. And it's approximately 2.71828 and so on. Um, so you just need to know that E has an actual value. It's not a variable, so you don't want to treat it as if it can change. It is a number. Um, if you have an exponential function that's written with a base of E, it's called the natural base exponential function. And it would be written something like this: f of x equals e to the x power. E would be the base because it is the number. The x is the values that change. That's your variable, so you can plug in. If you have a logarithm with a base of e, it's called a natural log or a natural logarithm. So for a natural log, it would be log base e of some number, we'll say x. Log base e of x. And let me put f of x out here. Now, the thing is, we don't write log base e. There is a more appropriate way to write it, so you will always see it, if it's log base e, you will always see it written as ln. That is understood to be log base e. Okay, so if you see ln, you know that it's log base e, so we would rewrite this as ln of x. So your function would be f of x equals ln of x. All right, and then all of the rules and properties that you've already learned in this unit for exponential and logarithmic problems, they all apply in this particular example. So let's take a look at the graphs. All right, the graphs here, notice that this is your exponential growth function because e is approximately 2 point something. It's greater than 1, so you have growth. And it's shaped just like the other exponential growth functions. The domain here, domain, all real numbers still. Domain, I'm gonna match the colors to the graphs. And in this case, we have blue for the exponential growth. So the domain is all real numbers. And the range, that is the set of y, such that y is greater than 0 still. All right. And then there's still an asymptote at y equals 0. And of course, for the logarithmic, the natural log here, the logarithmic function, it still reflects over the line y equals x. They are inverses of each other. Your domain here now becomes the set of x values, only the ones that are greater than 0. X is greater than 0. And the range is all real numbers. It's going to go all the way down, and it's going to continue to grow up, 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 up as you pick larger x values. So all real numbers. And the asymptote for a logarithmic function is it's on the y-axis, so it's at x equals 0. So notice nothing has really changed. You're just using a different value for the base. So that's really all E is. E is just a number. If you were graphing, again, you just graph just like anything else. So you'd pick some values for the x. They chose -3, -2, -1, 0, 1, 2, 3. When you plug it in, of course, because E is irrational, you're going to have to round. So figure out what e to the value is. whatever you picked, and then add 2 to it and round it. Of course, they got this shape here. You just plot the points just like you would graph any other exponential function. Okay? All right, let's move on. All right, so let's talk about converting. So here we have e to the x equals 24. Well, the same rules apply. If I wanted to write this out as a logarithm, I would say log base e of 24 equals x. But remember, on the first slide I told you we don't write log base e. So the more appropriate response would be ln 24 equals x. Okay, over here I have ln of 6 equals x. Now, if I saw this as a logarithm in general, like we used to see it, you would see log base e of 6 equals x, right? And so you would say e is the base to the x power equals 6. Same thing that we did in the last class, you just need to remember that ln it's a log with a base of e. The properties, you apply them the same way. So we're adding here, and these two are both natural logs because they both have a base of e, and so we multiply the values here. So we get ln of 48, and you're going to have to simplify this, but this will not be a value that you'll know in your head because the base is an irrational number. So some irrational number to a power gives you 48. So in that case, you take your calculator and the ln button is just to the left of the number 4. So you'll see the letters ln, okay? If you press ln, again, right next to the number 4, ln 48, and that's going to give you approximately 3.87. I'll leave it rounded there. This would be applying the property, but if you wanted to evaluate, I'm going to put evaluate. That's an A there. Evaluate. It would be approximately 3.87. Okay, over here, now in this one, because we have this 2 being multiplied by the log, we need to put it back in its home. It's been powered down. You want to put it back up there. So we have ln 63 minus ln 3 squared. Well, let's go ahead, since we know what 3 squared is, let's go ahead and simplify that. So we have ln 63 minus ln 9. And since we are using the same base and subtracting, we can divide the numbers here. So ln of 63 divided by 9, and we know that that is 7. So ln 7. So basically what we're saying is e to some power is 7. And we don't know because e is irrational. So if we wanted to evaluate it, we would type in ln 7, and we would get 1.95 approximately. 1.95. Okay, let's move on. All right, now we want to solve equations. The goal for solving equations is to get rid of anything that's hindering you from finding out what x is. So I have a logarithm on both sides. If I do something to one side, I must do it to the other, unless I'm just applying a property. Well, in this case, I have a log base e. That's a natural log. In order to get rid of the log so I could get inside there to get the x, I have to make all of this go into the exponent, and I need to use a base of e. So I'm going to write e to the ln 4x minus 27. Have to do the same thing on the other side. E is the base to the ln 15 minus 2x. Now again, the reason for doing this is because I'm trying to undo the logarithm. So exponents will undo logarithms. So these cancel because they both have a base of e, and I'll be left with 4x minus 27 equals 15 minus 2x. I'll move my 2x to this side. If I add 2x, I'll get 6x. I'm going to add 27 here, so add 27, I'll get 42. And then if I divide by 6, x equals 7. And if I plug 7 back in, 28 minus 27, because I said 7 times 4, so 28 minus 27, that's 1. And over here, 15 minus 2 times 7 is 14, so 15 minus 14 is 1. So we have a log of 1 and a log of 1. So those both equal each other, natural log of 1. All right, this one's a little bit different. If we're just trying to figure out x, well, we've got a lot of stuff going on with the x. Well, first it's up in the exponent, so I'm going to have to get rid of the base, but I can't do that yet. It's also being multiplied by 4, and then there's this plus 2. We're going to start with getting rid of the plus 2. Always start with the order of operations backwards. So we have 4 times e to the x power equals 178. And we're going to divide by 4 to get the 4 away from that e to the x. Let me extend this page here. Cancels here. I have e to the x power equals 178 divided by 4, 44.5. Now, in this case here, I'm trying to get e. I need to get rid of it because I'm trying to get to the x. So the only way to get rid of a base of e is taking the natural log of both sides. So if I write ln e to the x equals what I did to this side, I have to do to the other side, ln of 44.5. Now that cancels here, and I'm left with x equals ln of 44.5. Now, ln 44.5, just type it in your calculator, ln 44.5, and that is approximately 3.80 if you are rounding to the nearest hundredth, because it's 3.795. So I'm just going to go ahead and round to 3.80. Okay, so the natural base e works just like any other base. You apply the properties the same way. If you have any questions, just let me know.